for the last presentation of this session by Wilma Dewald, application of ultra-thin glass in cars. So this will be quite interesting for everybody. So first short introduction. Wilma Dewald studied in Göttingen and in physics and got a PhD from the Fraunhofer Institute of Surface Engineering and thin films in Braunschweig. And since 2013, she's working on glass topics within Volkswagen in the innovation groups. And yeah, it will be quite exciting, I guess.
Yeah.
Thank you very much.
Thank you very much. Yeah, well, I'm very happy. Let's see. Okay, there it is. I'm very happy to present you some results we gathered in a joint project over the last 3 years. It's dealing with ultra-thin glass, and yesterday I've been in a session where somebody said, what are you doing with that skinny 8mm glass? Actually, we're going to be far thinner here. I'm talking about 100 micrometer of glass, so we are not really in the architectural glazing area anymore. And I have some co-authors here who also participated in that project. So to name Fabian Unterse-Wilms from TESA and Dr. Regine Niepmann from Flabeck, and also a PhD student from University of Braunschweig took part. So what we are doing at Volkswagen in group innovation is we are doing scouting on new technology. And here you see the spread of our innovation hubs. I'm located in Wolfsburg, which is the headquarter of group innovation. And yeah, I don't want to bother you too much with that details, but the project I will present here was focusing on confection of ultra-thin glass for various applications. I will focus today on automotive application and the lamination process and coating, but there are several more steps. And if you're interested in these, some of our partners are here at GPD as well. So Suragus has a booth outside, and also Fraunhofer FEP is giving some talks also about coating. So let's go into the application. What could we do with flexible glass, which is so thin that it behaves like paper? There are several ideas we had, and the question is, does this glass survive the stresses we see in the field? Actually, if you want to cover sensors, it has to be transparent, it has to be not only scratch resistant, but also survive stone impact, especially if you're in the bumper region. So that will be one of the first tests, if a laminate with ultra-thin glass survives stone impact. If we go on top of the car, we usually use LiDAR sensors for autonomous driving cars to scan the surrounding by lasers. And therefore, you have these ring lenses on top, so very, very small bending radius. Is it possible to bend glass in that range? And for interior, well, inside a car, most surfaces are not just 2D or flat, they are curved spherical along 2 axes. So we really need 3D bending, which cannot be done by cold bending. And the question is hot bending possible with that thin glass? If you think of gravity bending, I mean, the weight is very, very low, so it might take some time. And finally, we could also think of the B-pillar, which is located between the front and the back door. You might have seen already some cameras installed there in some cars, and in the future it might also be an interactive medium where you have a display, some information, and so on. And if you use glass as a cover, it's always nice to have it lightweight. So there are some critical tests, and I will just follow them step by step in the following slides. If you haven't heard about ultra-thin glass before, here's a short summary what you can expect about curvature and bending, cold bending. So the formula is given up there. The tensile stress can be calculated out of the Young's modulus, thickness, and the radius you are bending. And as you can see, the thinner the glass, the smaller the bending radius can be. So depending on the application, you can choose if you go for 100 micrometer glass or 50 micrometer glass. And I just put the suppliers we had a closer look to, so Nippon Electric Glass, Schott, and Corning, who all have own products. Yesterday I learned that also AGC has a rolled glass and portfolio, so there are probably more suppliers in the chain, but we only had a look onto these. And the material itself is borosilicate glass. It's not chemical strengthened, so it's just pure glass, very, very smooth surface. And what makes it so unique is that it's flexible, scratch resistant, and also chemically very robust. And this is what we want to use, for example, for encapsulation of OLEDs. It's very good to have a diffusion barrier, and you can have everything with this lightweight material. But let's see how strong it really is. So I would like to answer the following questions. Does it survive stone impact if we have such a laminate? Which thickness? We just had a brief look, but we will go into detail what to take for a 50 millimeter curvature range. Then hot forming would be interesting if it's possible, in 3 dimensions if possible. And of course, functional coatings are also topics. So if you want to have touch sensors on that glass, some silk printing, whatever you can think of, you can just functionalize the glass and attach later. And well, if we think of the B pillar, then there might be a moderate pressure if somebody touches it or bumps against it, so it has to survive. And finally, I'm not talking only about glass-to-glass lamination, it's also about plastics and glass, so you have a hybrid laminate. And if you change temperature in climate change tests, that's a really substantial stress for the sample. So let's start with stone impact. Here you see a flat sample. So it's 100 micrometer glass laminated by a 50 micrometer thin acrylic tape from tesa to 2 millimeter polycarbonate. And we already heard this morning how stone impact test is working. So you shoot small stones, which are quite sharp, with 2 bar onto that sample. Angle is 45 degrees. And then you see the image. And unfortunately, the glass is damaged. So it's not really surviving. Imagine if this would be a sensor cover with transparent polycarbonate behind. You wouldn't see too much through it anymore. The same for the ring lens. It's not only that the glass gets some impact, it's also delamination you see here. So it's not a good idea to use such laminates in stone impact areas, in the bumper and exterior. So we have to look for different locations. And talking about the ring lens we just seen, you should choose 50 micrometer for that, because if you are following the line of 50 millimeter radius, you can assume maybe 50 megapascal breaking point here. That can depend heavily on the quality of glass edge and surface. But Nippon Electric Glass gave that range approximately, so I took it here as well. And if you just follow it, for example, for a 100 micrometer sheet of glass, which would be the orange line, then you see you're above that breaking point already. So for these small bending radius, you have to be as thin as 50 micrometer. But that's available on the market, and you can buy rolls which are 300 millimeter wide and are really wind up for several meters. And there are also companies working on equipment, how to code it, so you can just roll and unroll and put ITO, for example, on top. So we talked a lot about cold bending, but what about hot bending? And our partner Flarbeck did some hot bending experiments for all these different glass types, different thicknesses. What you see here is an 0.55 millimeter thick soda lime glass with different curvatures, and it worked quite well. So this is working as long as it is just bending over one axis. But if you want to get really three-dimensional, we end up here. You see some wrinkles, and at least with gravity bending, with the existing tools, it's not surviving. I mean, it's not helping that the glass gets stiffer if you cannot do any lamination with such a wrinkled something. So we just discarded the idea of getting three-dimensional forms in that dimension. Let's say I think it's 300 millimeter in size and 150 millimeter. So maybe if you have smaller samples, it might work more easily, but here, at least with gravity bending, there's a stop. Yeah, but functional coatings like screen printing here works quite well as long as you choose an ink which is not shrinking too much. So if you cure the sheet, the layer, then you might have the problem of curvature again. Some people of you might know that this very thin glass is used in laboratories to identify an intrinsic stress in the films. Which is nice for analytics, is not helping us if you want to apply several layers and have to think of internal stress for all of these layers. So there has to be some work done to move on. For example, here we try to have some symbols for OLED illumination, and before curing it's completely flat. Printing is nice. After curing you had this curvature, and well, so the second layer is a problem. All right. Now let's go to the application of B-pillar. Here we thought, okay, what is a good value? There's no standard test in finding out what about pressure and so on. So we just thought, okay, we take a 100-gram ball, let it drop 50 centimeters. That might be a good rule of thumb. But we didn't have a 100-gram ball, so we took a smaller one. That's why we have these uneven numbers here. The kinetic energy is the same, and you see if you go for polycarbonate, it survives all of the heights, so up to 1.5 meters. If you just take untempered glass, it already breaks at 56 centimeters, so it's not so stable. I mean, if you temper it, it's better, of course, or if you make it thicker. And if you go for the laminate, you see it's far stronger than just pure glass. But you see a slight damage at the maximum kinetic energy we chose here. But I think it's still kind of okay. We tested the limits here. Ball drop test, so moderate impact on such laminates will be no problem. What will be a problem is if you change temperature between -40 degrees and 80 degrees, and several times cycling these temperatures, which will occur in the field later on. And you see, especially at -40 degrees, that's the picture on the left side, there's a bending over two axes. And as we know, that's a problem for ultra-thin glass. So it's only flexible in one direction. And in the end, I hope you can see the contrast. You see a lot of cracks and also delamination after these tests. So unfortunately, the sample size, 40 by 20 centimeters, was too big for the combination of polycarbonate and glass. So what you could do is, if you go for that hybrid laminations, make smaller samples, or just laminate glass on glass. So we also talked a lot about retrofitting facades, for example, or retrofitting glass anyway. As long as you stay on a junction glass to glass lamination, it's no problem at all. But if you go for plastic and glass, keep in mind not to be too big. Yeah, so to summarize my talk, we could answer some of these questions. The stone impact test was not passed. The glass thickness for such small curvature, like 50 millimeter, would be, the best choice would be 50 micrometer here. Hot forming is especially possible for two-dimensional geometry. Three-dimensional is still something we have to work on. And screen printing in principle is fine as long as you choose the right inks. So ceramic inks, for example, are not working very well. You have to go for organics. And well, the ball drop text, I would say it was quite fine. And yeah, we just have seen the climate change test. So as long as your sample is small enough, no problem. If it gets too big, then you get these different thermal expansion coefficient problem. And so if we have a look on the applications, some of them are out of scope. So stone impact or head crash areas I would avoid. Small samples, as I said, are okay. And three-dimensional geometries for now are not possible, but this is something we can challenge maybe you as glass industry, how to handle this. And the challenges I would like to hand over to you is especially glass handling for this very thin glass, because it's not so easy to have a vacuum handler or to clean it, for example. There are all these steps you already know for architectural glazing, which are solved, but also shipping and all the steps in between, they are all increasing the risk of breakage, and then the yield goes dramatically down. freeform cutting. We had some nice talks about laser cutting here, and cutting of laminates would also help roll-to-roll production of laminates, would make it much cheaper in the end. And yeah, well, the old story of good edge quality will always be there. So thank you very much for your attention. And if you have questions, I will be around.